Hey guys, so today is Monday the 16th. It's an A day. Hope you guys had a good weekend. I'm gonna go ahead and make my videos for next week, for this week since I'll be out. So we're gonna do some free response kind of practice. So we'll start with this one. This is an easy one. So we've got a reaction here. Nitrogen is combining with ammonia, or nitrogen is combining with hydrogen to form ammonia. Ammonia is NH3, and you guys do need to know that. That's ammonia. Okay. We're given the concentrations of each of these. So we're told that NH3 is equal to 0.0272. We're told that the concentration of N2 is 0.0402. And the concentration of H2 is 0.1207 molar. And so we want to find the K value. KEQ or KC, we want to solve for this. So we're going to do products over reactants. So my product is NH2. We're going to square it because the coefficient is a 2. Remember that the coefficients in the balance equations become exponents in the K expression for the equilibrium constant. Okay, and then we're going to do reactants on bottom. N2 is just 1 for the coefficient, right? Because that's a 1 there, because there's nothing. And you got to make sure that these are balanced, and this is a balanced equation. And then H2 is cubed. So we are going to plug our numbers in. 0.0272 squared divided by 0.0402 to the first times 0.1207 cubed. All right, and so when we plug this in, we'll get a Kc value of 0.105. All right, and what I want you guys to do with this problem to make this useful for you, okay, to get some benefit out of seeing me do this problem, is I want you guys to plug that in your calculator and get that number. Practice doing that, because if you don't practice it, come time for the equilibrium test that we'll have in a month or so after Thanksgiving, if you can't do this in the calculator correctly, you won't get the right answers, or you'll miss them on the AP test. And so I want you to practice that. So this gives you a chance to practice that. So you're going to square this number on top, and then divide it by this number, and then divide it by this number cubed. So that is tricky to type in the calculator. You can type all of that in one line on the calculator, but you have to do it very carefully. Lots of parentheses, okay? And I don't recommend doing that because there's a lot going on here. I recommend doing it in steps. The more steps you do, and I know this is a pain, but the more steps you do for a problem, the less likely you are to make mistakes. Okay, and I actually did a problem earlier. I did it like 5 different times, and it really got irritating. And I didn't get it correct until I did every single step. Every single step I had to write down by hand to do, otherwise I would miss something, and I'd end up getting the wrong answer. I did not get the correct answer until I did every single step. And that's not always the case, but on that example, it was. And that was the quadratic formula. So that's a pain. Yes, there are some questions that we'll see on the AP test with the quadratic formula. Not many, though. And there is a shortcut to that method, and it usually works. So, okay, so there's that one. That one was pretty easy. If you're given an equation and initial, now these are equilibrium concentrations, okay? So at equilibrium, this is the concentration of NH3. This is the concentration of N2. This is the concentration of H2. So if you're given initial equilibrium concentrations like we are here, you plug them into your equilibrium constant expression and solve for K. And so that'll be your equilibrium constant value. at a certain temperature. If we were given initial concentrations, we have to make a rice table. So let's see how to do that. All right, so let's do the next one. I'm going to call this example 2. All right, we got 2, actually I'm going to move this down a little bit. 2SO3, and I think that's a gas, is going to be in equilibrium with 2SO2, which is also a gas, plus O2. All right, so when you make a rice table, it's RICE. Okay, R for reaction. You write the balance equation with the coefficients correctly there. You write initial conditions, initial pressures, initial concentrations. C is for change, it's not for concentration, it's change. That's the change in the concentration. And then E is for equilibrium. Okay, so that's our chart. When I do this chart, let me get rid of that one. When I do this chart, I will usually put a line underneath change, and it's kind of like adding. I'm going to add these two together. I take the initial concentrations, I add the change to get to equilibrium, and then I get equilibrium. All right, so initial concentration plus the change in the concentration, or pressure, if it's pressure, equals equilibrium concentration. Okay, so you add those up. We're going to do that for each of our species. And I'm going to use that word. I hope that's okay. A species is a thing. That's one thing that's a species. So there's 3 species in this reaction. There's SO3, there's SO2, and there's O2. So those are reactants or products species. So a term we like to use. And I've been using it a little bit. I hope it hasn't been confusing you. All right, so we are told that our initial concentration is 6.09 times 10 to the minus 3. We have none of this. We have none of this. And we may have done this one in class, and I hope we didn't. But we may have done this one in class. If so, we'll just do it again real quickly. And then we're told the equilibrium concentration. Let's see, what were we told here? I'm trying to remember here. I think we have to be told the final equilibrium concentration of this guy, 2.44 times 10 to the minus 3. So this is what we're told. So we have a vessel, we have a flask. It has these 3 gases in it. Actually, rather, it just has SO3 in it. So it's got SO3 gas in it. And so basically what happens is it breaks down on its own, and it'll split into SO2 and oxygen gas. So when we do start this reaction, it is sealed. It's a closed system, and it just has SO3 in there. But as soon as it's in that sealed chamber, it'll break down. So initially, we have all SO3, a reactant. We have no products. And so we immediately can assume, since there are no products, we need to reach equilibrium. And so which way is it going to head to reach equilibrium? There's only one way to go. You only have reactants, so the only way to go is forward. Okay? And we got to be careful here because I don't want y'all to assume that the reaction is going forward. But if you don't have any products, if you're told that your concentrations of your products is 0, then you can assume that it's going to make products. Because in order to reach equilibrium, you need a little bit of everything. You need the right amount of everything for it to be balanced. Equilibrium is kind of like a balancing act. You need a little bit of everything. All right? And so we're going to assume that the reaction goes forward. That means that the change in the concentration of my reactants will be minus, just like in kinetics, how the rate was minus, because you're going to be using them up. So we're going to use up a certain amount of that SO3, and then we're going to add these guys. They're going to be positive. And so watch your signs on the change. If it's going to the right and the equilibrium lies to the right, or the system has to shift to the right to get to equilibrium, it's going to be minus for the reactants and positive for the products. If the reverse were true, if the equilibrium was shifting to the left to reach equilibrium, we would flip the signs. Okay? And I don't know if I have an example like that, but we'll see. So how do we do this on? Well, the initial concentration is this. The final concentration is this. So let's find the difference in those values. Plug it in the calculator. 6.09 times 10 to the minus 3 minus the 2.4 times 10 to the minus 3. And we get 0.00365. Okay, so we know that that's the change in that one. And then we can use the stoichiometry here to determine the change in the other two. And I think I'm going to stop at this one because now I'm pretty sure we did these together. But it's good to do them again. But I'm not going to do the rest of them. I'm just going to do this one. So there is our coefficient here for that one. And then the coefficient is the same for that one. So since they have a 1-to-1 ratio, I can assume that if I take 2 moles or 2 molecules of SO3 and it breaks down, it's going to make 2 molecules or 2 moles of SO2. And so the same amount will react. Every molecule that reacts will make a molecule produced, right? So that's going to be plus 0.00365. And then the oxygen will be, looks like I messed this one up. Oxygen will be half of this. So it'll be half of this. And what is half of this? Looks like I messed this one up, so it's good that we're doing it again. 0.00365. So that's going to be that divided by 2. So that's going to be 0.001825. And I might have done this one right in the video, but I've got it on paper here and it's not right. All right, so that's correct. So let's find out equilibrium concentrations. For SO2, right here, we start with 0, we add this, and so we just get 0.00365. Right? If you start with 0 and that's what you add, then that's your equilibrium concentration for SO2. And then same thing here, 0.001825 will be O2. So these are our equilibrium concentrations. So let's find our K value. All right, and I'm going to have to erase this. So I'm going to erase it in 3, 2, 1. Okay. Because I need some more room. So Kc will be equal to the concentration of SO2 squared times O2 to the first divided by SO3 squared from the balanced reaction. Let's plug in our values. I'm going to do it down here so I have room. 3.65 times 10 to the minus 3 squared. So this is the 0.0065 or 0.00365. I don't know why I switched it to scientific notation at this point, but I did. Let's just write it the other way. 0.00365. We're going to square that. We're going to multiply by the 0.001825. Actually, so I just had one thing on my paper that's wrong, but I ended up using the right number. So that's funny. So I ended up with the right answer, and that's why I didn't catch it. I was like, I would have caught that because I had the answer key for this one. I remember checking it. And so I had the wrong part in the rice table, but then I used the right number. So that's funny. All right, so then we got 0.00365 squared. When we plug this in, and again, guys, please practice plugging these in, we should get 4.08 times 10 to the minus 3. So plug this in your calculator. All right, use a graphing calculator. That's an app on your phone on Android called Graphing Calculator. And if y'all need help finding that, let me know. But use a scientific calculator, plug this in, and see if you get that value. And that will be our equilibrium constant value. Okay, and so since I did these questions already, I'm going to skip them. Because I remember doing this one. I think. I don't know. I think so. So let's see. Let's get to one that we have not done. Now I got my papers all out of order. I think I was going to do 13.10 first. Not that one. That's last. I think this is the correct order. Nope, that's last. I had these in order, now they're not. 13.10, 13.9. Okay. Okay, so here's 13.9. Let's do this. And I'll pull up the question so you guys can see it. Let me find it. If we go to Google Drive, I put them on my Google Drive. I don't know which one's which. That's not it. It's probably this first one. There we go. So let's download this one and rotate. Okay, no, that's not it either. Sorry guys, let me find it. That's not it either. Where are you? 13.9. Maybe it didn't get in here. Here it is. Okay, so calculating equilibrium pressures 2. At a certain temperature, a 1 liter flask initially contains 0.298 moles of PCl3 and 8.7 times 10 to the minus 3 moles of PCl5. After the system has reached equilibrium, 2 times 10 to the minus 3 moles of Cl2 was found in the flask. Gaseous PCl5 decomposes according to the reaction. So there's our reaction. And so that's what we're told. So let's go ahead and solve this one. Okay, so here's our reaction. PCl5 will break down to form PCl3 plus Cl2. Let's do our Rice table. 8.7 times 10 to the minus 3. 0.298 and 0 of that. Okay, and then we're told at equilibrium. Let me double check the question. We know that, and then we know that the moles of Cl2 is produced. Okay, so this is going to be 2 times 10 to the minus 3. Okay, so in this case, we are told the amount of PCl5, which is a reactant. We're also told the amount of PCl3. So they tell us you've got this much of the reactant, you've got this much of the product. They're going to reach equilibrium, but you don't know which way to reach equilibrium. Okay? And so the first step is to determine which way equilibrium is. All right? The way that we're going to do that is Q. Let me see. Maybe I'm not thinking about this one right. Okay, so let's find Q. Q is going to be equal to PCl3 times Cl2 divided by PCl5. All right, let's plug that in. PCl3 is 0.298. That's 0. PCl5 is 8.7 times 10 to the minus 3. And nothing is squared because we don't have any coefficients. And so that's 0 divided by this, which is still 0. So Q is equal to 0. So it's going to shift to the right. And we could have assumed that at the beginning because we have 0 Cl2. So I guess we could have assumed that, but I thought that this was one where you're given the reactants and products concentration initially, and then you got to tell which way it shifts. So we'll do another one like this, but this one shifts to the right. And so what we're going to do is we're going to say that it shifts to the right. So that means that this will be a minus change. We don't know what that value is. And this will be a plus change. And this will be a plus change. Okay, and so we need to learn how to write it in terms of x's, meaning that we don't know what the change is. All right, so this one is where, let's see, do they tell us the k value? We're looking for the k value. No, we're looking for the concentration of all species. We want to know the concentration of each reactant and product. We already know Cl2, so we want to know the concentration of equilibrium for PCl5 and PCl3 and the value of K. Okay. So usually they'll give you another problem where they will tell you the initial concentrations of a couple of the species. They'll tell you one of the species at equilibrium. They'll tell you the K value, and then you've got to find everything else. So what we do is we put minus X for reactants, plus X for products. Now, if this was a 2 here, it would be plus 2x. Okay, so you're going to add that change, but it's going to multiply by that coefficient. Okay. But in this case, we know the equilibrium changes. The reason we know them is because we were told the equilibrium concentration of chlorine. So we already know that the equilibrium concentration of chlorine is 2 times 10 to the minus 3. And we know that, so we know the change. We know that the change in this is 2 times 10 to the negative 3 because it started with 0. And that's what where it's at now. So that must be the concentration change. And then this one is 2 times 10 to the 3. And this one is minus 2 times 10 to the negative 3. All right, so then we calculate that. 8.7 times 10 to the minus 3. That's a minus there. Minus the 2 times 10 to the negative 3. We get 6.7 times 10 to the minus 3. We get 0.3 molar here. So now let's write K. Kc, or Keq, is the concentration of Cl2 times PCl3, all divided by PCl5. Let's plug those values in. 2 times 10 to the minus 3, 0.3, and then on bottom we have 6.7 times 10 to the minus 3. We plug all that in. Again, guys, please practice doing this. This one's not too bad because nothing's squared. So this is going to be 8.96 times 10 to the minus 2. And that'll be our K value at a certain temperature. All right, so that's 3.9. Ooh, here's a good one. And this is the last one I'm going to do because I'm getting tired. Okay, I've been working so much today trying to get ready for the baby so that I can actually take the time off, you know. Okay, so this one's good. I hope this one makes sense. Sounds pretty easy. We were told the initial concentrations and the equilibrium concentration of one of the products. So then we can say, okay, the reaction goes forward. And I even calculated Q, and you guys saw that Q was less than K, so Q needs to go to the right to get to K, right? Q needs to go to K, shift to the right. So we saw that. And the next one we're going to have to see in the next example, we'll actually have to find Q in order to determine which way it's shifting. We can't assume anything, okay? So let's try that. This is 13.10. Let's find it. Okay, here it is. Carbon monoxide reacts with water or steam to produce carbon dioxide and hydrogen. So that's the reaction there. Notice that they're not giving us the balance equation. I'm writing the balance equation, and there it is right here. But notice that they don't give that to us. And so you got to be prepared to write that reaction and balance it from the little bit of information they give us. They tell us carbon monoxide, it's CO. Remember, you put mono in front of the oxygen. Mono means 1, so that means 1 oxygen. And then when we say carbon, that means 1. If they said di, then it would be 2. Tri would be 3. And then it reacts with water, steam, and then it's going to produce CO2, carbon dioxide, and hydrogen. And you got to remember that hydrogen is diatomic, H2. Okay, so you got to remember your diatomic gases. At this temperature, 700 Kelvin, the equilibrium constant is 5.1. Calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1-liter flask. Okay. How do we do this one? This one's a monster. It's not the worst, but it's That's a little tricky. So let's write our reaction. So RiCe. We put a line there. Remember that we're going to add those. Our reaction is CO plus H2O is in equilibrium with CO2 plus H2. All right, we're going to start with 1 molar. How do I know it's 1 molar? We had 1 mole of each substance in 1 liter. 1 mole over 1 liter is equal to 1 molar. Okay, so that's 1 molar this, 1 molar this, 1 molar this, 1 molar this. Okay. We're not told the equilibrium concentrations of anything. Okay, we don't know the equilibrium concentrations. Okay, and don't get freaked out yet, but we don't know the changes either. All we know is K. K is 5.10, and we can totally solve this one. Okay, we don't know what Q is. We got to find Q. Now we can find Q with what we got. Okay, and so what we're going to do is we're going to find Q with the initial concentrations, see what that is, compare it to the K, see are we shifting to the right, are we shifting to the left. We're going to fill in our changes with X's because we don't know the change. And then we're going to take the initial and add or subtract the change to get equilibrium. And then we're going to write our K expression in terms of these unknowns and then solve for the unknowns. Okay. Okay. So let's find Q. Q is the reaction quotient. It is the same thing as the equilibrium constant expression, but it's written in terms of initial conditions. So what we're going to do is we're going to use these guys. It's the only thing we know. So we know that it's equal to the concentration of CO2 times H2. And you can check this equation's balanced. And I would check that, make sure you got a balanced equation so that you get the right exponents in your K. We're going to plug these in. 1 times 1 over 1 times 1. 1 times 1 is 1. 1 times 1 is 1. So Q is equal to 1. K is 5.10. So Q is equal to 1. K is equal to 5.10. Okay. So I got to erase my Q expression over here. So Q is less than K. Q is less than K. So write it on a number line. Q is less than K. Right, as you go to the right, you get positive. So that means that Q needs to get to K. So this means it's going to be a right shift. Okay, so when it's a right shift, what do we do with all these question marks? I'm going to leave the equilibrium ones as question marks now. All right, so if we're going to shift to the right, we're going to consume our products, or our reactants, and we're going to make products. So that means that the equilibrium needs to shift that way. So this system is not at equilibrium. It's got 1 molar of each of all 4 of the substances, all of the species, and it's going to shift to the right to reach equilibrium. And so we're going to consume the reactants. And so I'm going to put a minus X, which means minus 1X, because there's a 1 coefficient there. And then same thing here. And it's minus again because it's a reactant. And then the products get a plus and an X. And the reason it's X and not 2X or 3X or 4X is because the coefficient is a 1. All these coefficients are 1s. And so I'm going to add 1X. Now, if it were 2, we would put 2 there. And we know that the change in the concentration would be twice as much because it has twice as much moles in the balanced reaction. So there's our things. Now, how do we get equilibrium? Well, we know that carbon monoxide starts with 1 molar and decreases by X amount. So let's write that, 1 minus X. And that's what we're going to put for CO. 1 minus X for H2O, 1 plus X for CO2, and 1 plus X for H2. Okay. Now, we're going to write the K expression. And I like this problem. K equals CO2 times H2 over CO times H2O. So that's kind of the expression, right? Let's plug in our values. CO2 is 1 plus X. H2 is 1 plus X. CO is 1 minus X. 1 minus X. Okay. And so that's what we got. We know K. K is 5.10. Okay, so this is 5.10. And we'll plug it in and solve it a little bit. Okay, so now we have 1 plus X times 1 plus X. So I'm going to write it as 1 plus X squared. And I'm going to write 1 minus X squared on the bottom. Okay. Okay, so that's our equation. Let's go ahead and try to solve it. Okay. I'm going to erase in 3, 2, 1. Or not. Just kidding. There we go. Okay. K equals 1 plus X squared over 1 minus X squared. And we know that K is equal to 5.10. So let's put that in. 5.10. So if I have two things squared on the right side, I can square root that side, and then I can square root the other side. And I can get rid of those squares. That'll clean it up a little bit. So the square root will cancel out with the squares. And then I do the square root of 5.1. That's 2.26. 2.26 is equal to 1 plus X over 1 minus X. And now it's an algebra battle. I hope you guys are good at algebra. So we have 2.26 is equal to 1 plus X divided by 1 minus X. So now what we're going to do is cross multiply. I'm going to do that times that and that times that. So I'm going to do 2.26 times 1 minus X. That's this part. I'm going to set that equal to 1 plus X times 1, which is just 1 plus X. So I have 2.26 times 1. I'm going to distribute here. I'm going to multiply the outside by both of the inside terms. So 2.26 times 1 is 2.26. 2.26 times X is 2.26X. And then that's equal to 1 plus X. All right, I have to combine like terms. So I'm going to add 2.26 to both sides. So I'm combining all the X's to the right side. So that's gone. So I have 2.26 is equal to 3.26X. I took the 2.26 and added the 1X right there. And I still have the 1 on the right side. So now I can subtract the 1 from both sides. It's gone on this side. So that is 1.26 equals 3.26X. And then divide both sides by 3.26. That's gone, leaving me the X. And X is 1.26 divided by 3.26, 0.38. Holy moly, 0.387. Okay, so we solved for X. We're not done. Okay, so we found X from this crazy equation. We took the K value. We set it equal to the K expression, although all of the equilibrium concentrations had X in there, but then we solved for X. Okay. And so you can square root both sides to get rid of the squares to kind of clean it up. We cross multiplied, and then we combined like terms. And you got to be careful when you combine like terms and do it right. I'm surprised I didn't mess it up just now. I'm a little rusty at this kind of algebra. Okay. So we know that the change in the concentration is 0.387. So let's go back to our rice table. I'm going to erase in 3, 2, 1. Or not. There we go. All right, so let's do our rice table again. CO plus H2O is in equilibrium with CO2, And H2, we know that this was 1, 1, 1, and 1. We know that the change was minus 0.387, right? 0.387 minus 0.387. Over here was plus 0.387 plus 0.387. And so this is 0.613 molar, 0.613 molar, 0.387 molar, and 0.387 molar. So what we would do for our answer is we would say the concentration of CO is equal to the concentration of H2O, and they're both equal to that value. So maybe box that value and say, okay, that's our number. And then the concentration of CO2 at equilibrium, and you can write EQ down there here if you like. I like doing that. That's equal to the concentration of H2 at equilibrium because they have 1-to-1 coefficient, and that's equal to that value. Woo! All right, there's our answers. So that's our concentration of our species at equilibrium. All right, guys, I'm going to stop there. I hope this was helpful. Please email me if you guys need anything. I will get back to you as soon as I can. All right, you guys have a great week.